Physics 1211, Lab 5, Moment of Inertia. In part 1, I'll be analyzing the motion of a marker, which is a cylinder, and a hollow ping pong ball, which is a hollow sphere, rolled down a ramp. The software I use is Tracker and GlowScript Python. Some key principles in this lab is rotational kinetic energy. Energy rotational is equal to 1/2 moment of inertia times angular velocity squared, and translational kinetic energy, which is 1/2 mass times velocity squared. Moment of inertia is dependent on size, shape, weight distribution, axis of rotation. In this picture on the bottom, you can see multiple different moments of inertia due to differences in size, shape, weight distribution, and axis of rotation. So here's the experimental video. You can see there's a marker, which is a cylinder, and the ping pong ball, which is a hollow sphere, rolled down a ramp. You'll be able to see that the marker made it down the ramp much quicker than the ping pong ball, and we'll get into that. So I obtained my experimental data by putting this video in the tracker and tracking the balls, and I got 2 graphs. We'll analyze them later. So here are the experimental graphs. And I will have to say there is a source of error that the camera is not in a stable position, is not showing the entire ramp at all times. This could create changes in perspective and makes the tracker software unable to get precise measurements. So here's the change in the x-axis that I found of each marker. You can see that the marker accelerates quicker and obtains a greater velocity towards the end. So here's the general synopsis of a ball and a marker. So the ping pong ball has a mass of 0.027 kilograms, a radius of 0.02 meters. It's a hollow sphere, and its moment of inertia is calculated by multiplying 2/3 times 0.027 meters squared times 0.027 kilograms, and you get that moment of inertia. The marker is 0.058 kilograms. It has a radius of 0.0127 meters, and the shape is a solid cylinder. And then its moment of inertia is calculated using this equation, and you get 0.0000467 kilogram meters squared for its inertia. And here's the ramp. It has a height of 0.7312. This is important because it helps us calculate the gravitational potential energy. So here's the GlowScript Python code I used to find the moment of inertia. So I plugged in the parameters for the ping pong ball and the marker, and then it came up with the moment of inertia at the bottom for each object, which is the same as doing the raw calculations. So now we can find with this information, we can find the translational kinetic energy. So what we do is we set gravitational potential energy equal to translational kinetic energy plus rotational kinetic energy, and you get that equation. And you can also set angular velocity equal to translational velocity over radius. Using conservation of energy, then we solve for velocity. We get the velocity of the ping pong ball at the end of the ramp is 3.363 meters a second, while the velocity of the marker is 3.773 meters a second, meaning the marker is moving faster. So some key points for this lab is the cylinder moves down the ramp faster due to having a smaller moment of inertia. This means that the cylinder has a smaller rotational kinetic energy, therefore having a greater translational kinetic energy. This makes its translational velocity greater than its rotational. Possible sources of error in the tracker video, like I said, the camera moved. This could change perspective. And the mass of the marker is not evenly distributed